second one is this, the middle one named as the B, then the last 0 named as the C. So then the first step, so this is the first step, we the convert the decimal value to binary value. So then the second step is, first of all, you need to write down the 8 zeros initialized to 0. So that step we called as the initialized to 0. 8 zeros. Then the second step is, you need to multiply this 12 by a value. By a value. A value is what? 1. A is the 1. A is the 1. So here the a value is the 1. This one. So you need to multiply this 12, binary 12 value by a value. So if we multiply this binary value by this a value, so 1 0 1 multiplied by 0, that is 0 here. Then the 1 multiplied by next 0, that is 0. Then the 1 1, that is 1. Then the 1, the first one, that is 1. The remaining zeros are keep same as it is. There's no any changes. So then that is the we called as a equal 1. So then you need to the next step is, you need to take the summation of the previous two steps. So what are the two steps? Previous two steps, initialize to 0 steps and the a equal 1. So then you need to get the summation of both two steps. So here 0 is 0, then the 0 0 0 here, then the 0 1 is the 1, then the 0 1 is 1. Then other remaining zeros are keep same as it is. That is the summation, first summation. Then you need to apply the left shifting. Left shifting. So left shifting means, so I will show you left shifting is, so this is the summation. This is the summation. So when you apply the left shifting here, so this 0 comes to this place. Then this 0 comes to this place. Then this 0, this 1 comes to this place. Then this 1 comes to this place. And other zeros place lie here. So now you can see there's a blank here. There's a blank here. So you can keep same as it is, or else it's better to put the 0 here. It's better to put the 0 here. So that is left shifting. So once you do the left shifting, then again you need to multiply this binary, this 12 binary value of the 12 by b value. So b value also same as the a value, that is 1. So again you need to multiply this binary value into b value. So you will get the something like this. So same thing, no? So the same answer, because the 1. So then once you done the multiplication, then you can get the summation of the previous two steps. So previous two step means these two, the left shifting and the multiplication by b value. So you will get the summation of both two values. So once you get the summation, you will get this answer, 0 0 0. Then the 0 0, again you will get the 0. Then the 0 1, that is 1. Then the 1 1. So 1 1 means 1 0. 1 plus 1, binary 1 plus 1 means a 1 0. So since it is the 1 0, we keep the 0 here and keep the 0 here and move that remaining one here. Move that remaining one to this place. Then here there is a existing one plus that previous one, 1 plus 1, again 0, then you put the 0 here and there is a remaining one, then remaining one comes to here. Then 1 plus 0, then 1. That is the summation. So you will get the answer like this. This is not the final answer, okay? So this is the sum. Then again, you can do the shifting, left shifting, same as previous. So here, so this 0 comes to this place, this one comes to this place, then 1 comes to here, then 0 comes to here, then this 0 comes to here, then this one comes to here and remain keep same as it is. So here, since this is the blank space, you can put the 0 here. So again, the next step is the C value. So then you need to multiply this binary value by C value. So C value means C is the 0. Then when you multiply by 0, then you will get the 0. 0. Then you can get the summation of the previous two steps like this, then you will get the final answer like this. Okay, so there's no shifting, again no shifting here because this is the last value, therefore no, we are not going to apply the shifting here. So once you convert this binary value into decimal value, definitely you will get the 72. Okay, so I think now it is clear to all of you.
Miss, could you explain that last step, the final step again?
Sorry, yes. So which one, Putta?
It's
This
the
one?
final step.
The final step is
So
the
the final answer is at 72?
no. Final
That's the
uh
decimal multiplication, right?
yeah. So the final answer is this one. This one, the 0 1 0 0 1 0 0 0. That is the final answer. So I told you if you are not sure about your answer, so you can just keep another paper and just try to convert this binary value into decimal value. Then definitely you will get the 72.
All right, Miss, thank you.
So if you get the another number, that means your answer is wrong. That means you may had some calculation issue in these steps. So otherwise, you will get this answer. That means according to the my example, if you get the 72 here, then your answer is correct. That's the thing. Okay, so I think there are no more questions regarding the binary multiplication. So let's move to our lecture.
Good morning, Miss. Is it possible for you to start recording the session?
Sure. Sorry, I forgot that. Okay, so today we are going to discuss about the digital logics part 3. So basically in this lecture we are going to discuss about the sequential circuit. So last week we discussed about the combinational circuit. So now today we are going to discuss about the some circuits which comes under the sequential circuits. So when moving to the lecture learning outcome, objective. So at the end of the today's lecture, you will be able to understand the latches, then the basic element of sequential logic circuits. So understand the use of clock signal, then the how flip-flops are working. Uh, so actually, we are not going in deep in these digital circuits. So we just touch those flip-flops, those circuits um, me- externally because these circuits have some deep processes. That means there are some deep steps here. Working steps are here, but we are not going that too much. So we just introduce the what is the flip flop, those things, and we are going to introduce some characteristic table regarding those sequential circuits. So then finally we understand the use of flip flops for registers. So these are the things we are going to discuss today's sessions. So latches, then the clock signal, then the flip flops, sequential circuits, and finally registers. Okay. So, are you familiar with latches? Latches, are you familiar? The latches circuits?
Yes, miss.
Okay. So, so when talking about the latches, basically latch is essentially a building block in digital electronics used to store a single bit of information. So this latch is basically used for to store the single bit of information. What is the single bit means? Single bit means one or zero. That is the single bit. We call it as the single bit. One or zero. This is we called as the single bit. Okay, so latches are basically used to store the single bit. And unlike the combinational logic circuit we discussed last week, latches have memory. Okay, so that is another important point. Unlike the combinational logic circuits, these latches have memory. So latches have memory means so latches comes under the sequential sequential logic circuit. So from that we can say sequential circuits have memory. All the sequential logic circuits have the memory. So combinational circuits haven't any memory, but when it comes to the sequential circuits, those logic circuits have the memory. So, so it converts the output according to its inputs instantly. So that means outputs are depend on the inputs. Then third point, latches can be implemented using various digital logic gates such as AND, OR, NOT, NAND, and NOR gates. So latches are built using various logic gates, as I mentioned here, and or not NAND, NOR gates. So and another thing is there are so many different type of latches. T latches are there, SR latches are there, T latches are there. There are so many different type of latches, but one of the simplest latches is the SR latch. Okay, so SR latch constructed using the NAND gate. There are so many latches. So the simplest one is the SR latches. Then latches have a wide range of application in digital systems. They are used for the data storage, then the control circuits, and as a part of the flip-flop circuits. So then another one is, do you remember the registers we discussed during the processors? There are some registers. So in there, latches are used to hold data temporarily within the microprocessors. Okay, so I uh, told you in registers we know we use registered in order to store the some data, small data temporarily. So in in order to store those data, these registers are also use the latches, because latches can store the single bit data. So therefore, registers also use these latches. Okay. So then they are often used in combination with other digital circuits to implement the sequential circuits such as state machine and memory element. So here implement the sequential circuits. So when it comes to the sequential circuits, last week we discussed the combinational circuits. So here today we are going to discuss about the different type of sequential circuits. So can anyone say what is the differentiate between the combinational circuit and the sequential circuits?
Sequential circuits have memory.
Sorry.
Sequential circuits can store memory.
Yeah. So how it is affected to the output? Can you say about that part? How it is affected the output of that particular circuits? So when we talk about the combinational circuits, if you want, you can note down. I will write here as well. So when talking about the combinational circuits, so our output of the combination circuits based on the current input, only the current input. Output based on the current input. This is combination circuits. So I use the CC, that is the combination circuits. So when moving to the sequential circuit, output that depend depends on both current input and past or the previous output. This is sequential circuit. How this sorry. Okay, how this this sequential circuit is going to access the previous output, because the sequential circuit has the memory element, so it is store the all the previous output there. So therefore, this this sequential circuit based on the both current input as well as the previous output, because of the memory element. But when come to the combinational circuit, since they have no any memory element, therefore it's only depend on the current input. But whatever we input that logic circuit, then depend on that input, it generate the output. But sequential circuits, it's depend on the current input as well as the previous one. This is about the differentiate between the combinational circuit and the sequential circuit. Okay, so then the first latch is the SR latch. So when talking about this SR latch is a very simple memory device. It's a very simple memory device that stores a single bit of data. So normally uh, the the purpose of using latches is uh, store the single bit of data, whether it is SR latch, whether it is the D latch, whether it is the T latch. So all the latches store the same thing. That means single bit of data. The SR in SR latch stand for set reset. S means set, S means set, then the R is reset. S is set, then R is reset. Reset. In shortly, we call that as the SR latch, but in long term is set reset latch. Set reset latch. So this SR latch has the two inputs and the two outputs. So here so here so these are the two inputs, the S and R, then the Q and Q bar. Q bar is the Q and Q bar are the output of this SR latch. So Q is the current stored value. Q is the current stored value, and the Q bar is its inverse, current stored value. So I will current stored value. Q. This is the Q. Q is the current stored value. Then the Q bar is, you already know, this is the Q bar, so it is the inverse. Then S and R are the input of this SR latch. And here you can see this is the okay. So before moving this one, can you say what is this logic gate? This gate, what is this gate here? This one, what is this gate? Anyone say? No. Yes, this is the NOR gate. Very good. This is the NOR gate. So here you can see, here you can see. So let's take this S. This is the S input. So you can see there is another input, the NOR gate. NOR gate has the two inputs. One input is the S. So I'm talking about the bottom one. Okay. So bottom NOR gate. So one input is S. Then the second input is the one input for this first NOR gate is the uh, S, and another input of this NOR gate is the output of the first NOR gate. Output of this first NOR gate, that or the top NOR gate. Here, when talking about this NOR gate, one input is the S, one input is the S, then the next input is the output of this first NOR gate. Output of this first NOR gate. Same as it is when talking about this top NOR gate, one input is the R, and the next input is output of the bottom NOR gate. Output of the bottom NOR gate. So that's why I told you so this has the deep process. These latches has a deep process, but here under this FC module we are not going to in deep. We are not going to explain in deep. Just keep these things remember. That means this SR latch characteristic table, as well as this diagram, this circuit diagram, logic circuit. Okay, so this is the way we need to draw this SR latch logic circuit. Okay, so then another important thing of this SR latch is the basic idea of this SR latch is it remembers previous output. So I will the basic idea of this SR latch is it remembers previous output until a new input is applied. So in previous slide also I told you the sequential circuit when it comes to the sequential circuits, the output of the sequential circuit depend on the current inputs and the previous outputs. So when it comes to this SR latch also, the basic idea of the SR latch is it is remembers previous output until a new input is applied. Until a new input is applied. So I will write down it here. Basic idea. The basic idea is SR latch previous output until a new input is applied. So this basic idea is the starting point of this characteristic table. That is the starting point. So let's move to this characteristic table. The first row, you can see S equals 0, R equals 0. So this first state we called as the first is first row. This one we called as the hold state or the keep state. Hold state or the keep state. So I will put the other name here. Hold state. Both are correct. So if you want, you can note down hold state. Keep state or the hold state. So this state is what no new input is given. No new input is given. So that means there's no new input. That means the S equals 0 and R equals 0 is what? Previous output. Those are previous output. S0, R0. That means the latch keeps or the holds the previous state. Keep or holds the previous state. So I will no input is no new input is given. No new input is given. Then second one, S equals 0, R equal 1. S0, R1. So this state we called as the reset state. This is we called as reset state. So when S equals 0, R equal 1, the latch goes into reset state. Reset state. Then output becomes Q equal 0. So actually you no need to worry about how this Q values become 0, how this Q value becomes 1. Actually, by looking at this circuit diagram, we cannot understand that one. So because it has the deep process. So don't worry about those things. So just remind this characteristic table and this diagram, circuit diagram. Sorry, logic circuits. That's enough. However, S equals 0, R equal 1, we called as the reset state. That is, we called as reset state. Reset state. This is reset state. So S equals 0, R equal 1, then we called as the reset state. So always if the latch is reset state, then it's generate Q equals 0 and the Q bar is 1. Q bar is 1. So always Q bar is the complement. Q bar. Q bar is Q equals 0, then the Q bar is 1. That is the reset state. So first state is the keep state or the hold state. That means no new input is given. S equals 0 or equals 0. That means it's depend on the previous output. That depend on the previous output. Then S equals 0 or equal 1. If the R equal 1, then it is comes to the reset state. Because we called R is the reset, no? Then R become becomes 1 means that it is reset state. So if it is reset state, always Q equals 0, then the Q bar is the inverse of the Q, no? So the Q bar is 1. Then another one is the S equals 0, sorry, S equal 1, R equals 0. So that means we call it as the set state. That is set state. So once SR latch becomes to convert into the set state, then output is the Q. Output Q is become 1. Then Q bar it is the inverse of the Q. Then it will be the 0. Q bar will be 0. So why it is set state? Because here the S value is 1. S is 1, R is 0, then the set state. Because S is belongs to the set, no, then the set state. So always, if it is come to the, if the SR latch becomes the set state, then the output is 1. Output become 1. That means Q equal 1, Q bar equals 0. If it's come to the reset state, reset state means the R is 1, but when it's come to the output, Q always 0. Q bar is 1.
Miss, just a question I have regarding the SR latch.
Yeah.
So, for example, the first gate for which the R is fed into, it expects the input of the switch R and the
Hmm.
output of the second gate
Yeah.
to get. But the problem is you can't really calculate the value of the second gate since the input is not really being pressed or anything. So, will that automatically be defaulted to 0?
Yes.
Okay,
Yes.
okay, miss.
So actually, as I mentioned previously, so this SR latch and also there are some latches D latch also there. So this has some kind of a deep process. Okay. So actually, since because the here also by looking at this circuit also, there are some difficult things we cannot understand because here this output is connected to the the top inputs likewise. So in here also this output is connected to the bottom inputs. So there are some difficult things. So just no need to worry about these things. So just keep the logic circuit, keep it in your mind and the characteristic table. And another one is when comes to the characteristic table. So keep these things in your mind. That means the so those the the first one, second one, third, and fourth. So that means the uh, what happened when come to the reset state, what are the values? When come to the reset state, what are the values of the SNR? When come to the reset states, then what are the values of SR when come to the set state? Then what are the uh, outputs? When come to the set state, then what are the outputs when come to the reset state likewise. Then, then another one is the last one that is S equal 1, R equal 1. So we call this state as the invalid state. This is invalid state. This is we called as the invalid state. The action is restricted combination. This is invalid state. So there are four states: keep state, then the reset set, and the invalid state. Okay, so that is set reset latch. So let's move to the D latch. Okay, so when moving to this D latch, D means the data. So say this one also same as the SR latch, and D latch also used in digital electronics to store the single bit of data, as I mentioned earlier. So all latches are used to store the single bit of data. So the D in this D latch stand for the data, or the we can some of them are used D as the delay, data or delay. So unlike the the previous latch, that means SR latch, the D latch has only one data input. So when we compare these SR latch and the D latch, so here it has this SR latch has the actually basically it has the two inputs rather than this sorry, apart from these uh, sorry, so apart from these inputs, basically it has the SNR. So, but when it comes to this D latch, there's only one input. There's only one input. So the reason, um, actually the D latch is designed to eliminate the restricted combination state. So the previous one, there's a state called the restricted combination. That means last state when the S equal one, when the S become one, then the this R become one, then it's move into the restricted combination state. So this D latch is presented. Sorry, D latch is designed to eliminate this restricted combination state issue present in this SR latch. Okay, so in order to that means avoid this state, it use this D latch. That means the D latch ensures no valid state. That means the no invalid state, unlike the SR latch. Okay, so when it's come to this D latch, so D latch doesn't have any invalid state, like unlike this SR latch.
Miss, what does D stand for? Is it data?
Data, yes. So data, or sometimes some of them say it's like a delay, but basically we call that as the data, D latch. Okay, so then when moving to the um, so wait. Okay, so when moving to this characteristic table of the D, um, this latch follow this D latch follow the input D. So if the D is 0, then the output Q is 0. Output Q is 0. Then the D is 1, D become 1, then the output is 1. So if so this D latch is only depend on the D input D.
And so, what is the purpose of this switch? Is it to just store a certain value? Or,
So this D latch,
yes, miss.
the same thing, students. So the every latch is used for the same purpose. That is store the single bit of data. That's all.
Okay, miss.
So there are different type of D latches, SR, D latch. Then there is another latch called T, the T latch. So all of the latches, the only purpose is the store the single bit of data because it has a small memory element. It has a small memory element. So in that memory element, we can store single bit of data. That's all. So then let's move to the clocking. Clock signal. Clock signal are used to maintain the desired timing in the circuit. So that means if you want to do something according to the change of the time, then you can use the clock signal for that. Okay, so clock signal uh, present by this like here. So this one. So this is the clock signal like this. Then this is the clock signal. So actually, we are actually trying to incorporate the clock signal to a latch and build the sequential circuit from that. So the current we are going to build from that is known as flip-flop. So by combining the clock signal with the with the latches, we are going to build the flip-flop. So if so these are the latches, no? So if we add the clock signal for the latch for a latch or the latches, then it becomes a flip-flop. It becomes a flip-flop. So in shortly, we can say latch plus clock signal. Flip-flop. So flip-flop is the another digital circuit. latch plus clock signal, it becomes flip-flop. Okay, so when moving to this flip-flop, so we earlier have seen SR latch. Okay, so we earlier have seen the SR latch. So SR latch will get the so let's take like this. So SR latch get the two inputs, S and R, then the Q and Q bar, two outputs. So then if we add another signal called the clock signal. So you can add this clock signal from to bottom or the top. So these are the SR. The blue color ones are the SR, and the top one, the C, is belongs to the clock signal. Then this whole circuit becomes flip- this becomes flip flop. Flip. This is SR latch. Then if we add the clock signal to that SR SR latch, then it become the flip flop. Okay, so when you have the D latch with D input and try to combine the clock signal to this, then that D latch will convert to D flip flop. D flip flop. So as it is, when we add the clock signal to SR latch, then it become a SR flip flop. SR flip flop. So since this is D, if we add the clock signal to this circuit, then it becomes the D flip flop. This is D latch plus clock signal D flip flop. So same as it is, if we add the clock signal to this SR latch, then it become a SR flip flop. It becomes the SR flip flop. And it becomes a device which can store previous data inside the circuit because of the clock. And also it will be able to maintain timing inside the circuit because of the clock signal. Okay, so this is actually so there are some here there are so many here. So here there are different of things. So please go through this one. So but summary, in summary, uh, the thing is if you add the clock signal into any latch, then it becomes the flip flop. T plus clock signal, D flip flop. S plus SR latch plus clock signal, so it becomes the SR flip flop likewise. Okay, So then these are the very important terms what are coming up with, which are coming up with clock signal. Okay. So just read this for a while. Read these four terms: state change, setup time, hold time, propagation delay. So read this.
Excuse me, ma'am. Your mic is muted.
Yes, I'm not saying anything. Okay, finish reading. So normally, when come to this clock signal, normally we draw the signal in this way. So the black color one, this one, we draw the signal like this one. But but the actual or the correct behavior or the correct representation of the clock signal is this one. This is the actual one. Actual or the correct clock signal. But in um, we draw the signal in this way. But it's not no worry. So both are correct. So I just want to say, but in real case, signal, any signal doesn't get a sudden increase like this. So this is the sudden increase. This is the sudden increase. And this one is the sudden decrease. So you can see this is a sudden decrease and this is a sudden increase. But in real case, signal doesn't get a sudden increase or the decrease. So considering this, you can say it is slowly increasing, then slowly decreasing. That is the difference between these two. Okay, so but both are correct. So I just want you aware. So this is the actual representation of the signal. So this is the correct one. This is rising or the increasing. This is falling. Sudden. This is falling. Slowly rising.
Miss, just a question I have. I'm a bit confused about the function of the clock signal for the flip-flop. So, when the clock signal is high, is that when the flip-flop can be updated? Is it like enable switch? So, when the clock signal is low, the values can't be updated, but when the signal is high, it can be updated. Is it something like that, Miss?
Yes, yes, that's correct. But the thing is here, under this slide, we are not going to introduce the enable the point here, but there's a enable point in this flip-flop. By the way, here we are not going to introduce that one. I don't know why. However, there's no any points regarding this enable.
I see, but the flip flop is just like a normal a storage system, except it uses a clock to enable and disable it. The
Yeah,
storage,
yeah,
right?
yeah, yeah, yeah.
Okay.
Okay, so then the first term is the state change of the clock pulse. So state change is the rising edge and the falling edge. So rising edge is this one. So this is we call as this part we call as the rising edge. That is positive edge transition. Positive edge. Rising means the always positive edge. Positive rising edge. Then next state is the falling. Falling is this one. Falling edge. This is falling edge. Falling means negative. It is negative edge. Rising and falling. Then next term is the setup time. So setup time is in order to do this kind of changes. So this kind of changes means what? The positive and negative, rising, falling. So in order to do this kind of changes, it requires some amount of time to set up for this transition. That time we called as the setup time. That is the setup time. Minimum time that D input must remain at constant value before the transition. So according to this one, so this time we can take the setup time here. So before the rising, before the positive transition, this is the setup time. And also before the negative transition, this will be the setup time here. This may change, but according to our example, so this can be the setup time for before the positive transition. Then this is the setup time before the negative transition. That is the setup time. In order to do the positive changes or the negative changes, it requires some amount of time to set up for the transition. Then hold time. Hold time. Hold time is minimum time that D input must not change after the positive transition. So once a quick transition happens, it's waiting or holding some amount of time. Amount of time without change in signal. So that time we call as the hold time. Once a quick transition happens, it's waiting or holding some amount of time without changing signal. That time we call as the hold time. Then the last one is the propagation delay. Propagation delay means the time between the clock input and the response. Clock input and the response is known as the propagation delay. The time between the clock input and the response, known as the propagation delay. So those are the four terms: state change, setup time, hold time and the propagation delay. Okay, so sequential circuits. So we can include the sequential circuits, that means the flip-flop inside our circuit diagrams. So then flip-flop work as a memory element, and we can convert our combinational circuit into a sequential circuit using a flip-flop. So combinational circuits have no memory, but when we add the flip-flop into the combinational circuits, then it can convert into the sequential circuit, because by adding this by adding the flip-flop, it becomes the, so by adding the flip-flop, so then it will have the memory element, then it becomes the sequential circuit. So here you can see, um, this is the combinational circuit. The things I told you, this is the combinational circuit. Then when we add the flip-flop, then it will become the flip-flop with the clock signal, then it will become the sequential circuit. Okay, so then D flip-flop. Did we discuss? Yes. Okay, then D flip-flop. So here, this is the C, okay? This is C. This is C. Okay, so here you can see the D input is here. This is the D input is here. So this is the complement of D. Sorry, here D. So here, but so wait for a moment. Yes, so this is the D latch, and we have already seen this before, but some little changes are there when it comes to the D flip flop. So this is the not get, and there are some gates are added. So that's okay. There are some actual little changes. So these are the further enhancement. So what it does actually take on the clock signal, and clock signal is provided for the both gates. So this is the clock signal, and this clock signal is provided, sorry, here the clock signal is provided to the both gate, this one and this, both gates. So earlier we have seen when D equals 0, then Q equals 0. So earlier, that means when moving to the this D latch here, D latch here, D equals 0, then Q equals 0, then the D equal 1, then the Q equal 1. So this will happen. Sorry. Yes. So D equals 0, then the Q equals 0, then the D equal 1, Q equal 1. So let's take that values 2 here. So here D equals 0, then Q equals 0, then D equal 1, and then Q equal 1. So I'm talking about this characteristic table. D equals 0, then the Q equals 0, D equals 0, then the Q equals 0. Then this will happen only if the clock signal is provided. Only if the clock signal is provided. Clock, if the clock signal is provided, then the Q D equals 0, then the Q equals 0, then the D equal 1, Q equal 1.
Miss, can I know what happens inside the component you and labeled a pulse detector?
Yeah, wait, I will explain. So clock signal, when the clock signal is provided, when the clock signal is provided, then D equals 0, then the Q equals 0. So Puta, can you put that question in the chat box? Then I will go. So then D equals 0, Q equals 0, then the D equal 1, then the Q equal 1. So then let's take, so clock signal is provided means, here clock signal is provided means, here let's take the clock signal as 1. Sorry, C. This is C1, then C. Then let's take, if the clock signal is not provided, not provided, that means C equals 0, then D equals 0, the same thing, then what happened? Q. Q means there is no out. That means latch keep state. So we call that latch or the keep state. Keep state. Same as when the C equals 0, then D, so D value become 1, then Q that one also latch. That means there's no output. Keep, that means no output. Output, or we can say that is latch or the keep state. So when the clock signal is provided, that means C means the clock signal. Here I put like this. C. C is provided, then the D0, D1, then D, if the D is 0, then the Q become 0, then the D is 1, then the Q is 1. So if the clock signal is not provided, so we take the same thing, D0, D1 here, then the Q is become no output or the latch or the it keep state. So this is the same thing. This is the same thing. Here C 0 0. Here the first one 0 0. Then the latch. Then 0 1. That means our second one. This one 0. Then the D value is 1. Then again latch. Then 1 0. 1 is here. This is the first one. 1 0. 1 0. 1 0, that is 0, this one, and then 1 1, that is 1. So these two clock signal is provided. The last two, the clock signal is provided. The last two. Then first two, clock signal is not provided. Clock signal is not provided. The first two. The first two belongs to the clock signal is not provided. Then the last two clock signal is provided. That is D flip-flop. Okay, when talking about this slide, the semantic symbol for the D flip-flop is shown here. So this one, um, this is the semantic symbol. So then flip-flops can be connected in series to enable the transfer of data bits from one flip to the next on sequential clock cycles. So series of D flip-flops can be connected together and we can create a shift register. So we can create the shift register. So series of D flip-flops can be connected together and we can create the shift register. So registers are built actually support of these flip-flops. Okay, so registers are built actually support of this flip-flop. So this is the sample image of the this one is the sample image of the shift register. So you can see in this shift register, D flip-flops are connected together. So these are the D flip-flop. So these flip-flops are connected together and this becomes the shift register. This becomes the shift register. And then if the Q output at the end of the shift register is connected to the D input at the other end of the register, the resulting is the ring count. So that means what? So when you combine this, here they are saying when you combine this Q output at the end of a shift register in the shift register, when you combine this Q output with the other end, that means with the other end means this D input at the other end of the register, the result is the ring counter. So it becomes a circle. So we can create something like a circle. We called it as the ring counter. So ring counter means there's a shift register. So in the shift register, Q output at the end of this shift register is connected to the D input at the other end. D input. This is the D input. No? So this is the D input. So if we combine this with the D input of the register, then it becomes the circle. So this circle we called as the ring count. That is, we called as the ring count. So ring counters are used for tasks such as construction of finite state machine. It's a finite state machine. Then let's move to the SR flip-flop. So we talked about the SR latch. So then when we combine the pulse detector or the clock signal to the SR latch, then it become a SR flip-flop. Okay, SR flip-flop. So this is the SR flip-flop and S and R inputs are provided with the clock signal. So this S and R inputs are provided with the clock signal. So then it's a flip-flop. It's a flip-flop. So here, so let's take, so I take clock signal as CK, clock signal, then S, R, and then Q. Okay. So here clock signal is there, then the SR inputs and the Q. Q is the output. So if the clock signal is provided, if the clock signal is provided, these two inputs can be taken out from Q only if the clock signal is provided. So clock signal is provided means it becomes 1. If the clock signal is 1, then S1 or 0, then you can get the Q1. Okay, SC1, R is 0, then the Q is 1. So this is, sorry, sorry. Yes. So then the next one is, if the clock signal is provided, then the SC equals 0, then the R equal 1, then you can get the Q0. Q value is 0. So then, so Lamai, please give a 1 minute. Okay, so then another one is, if we provide the clock signal but S input is 0, then the R input is 0, then this Q output is non-functioning. This is non-functioning. That means it is latch. It is latch. The flip-flop is not functioning. Then I will, then if the clock signal is provided, then S is 1, then R is 1, then this is we called as restricted, or this is prohibited. Prohibited. This is
Miss,
prohibited.
wasn't the latch thing called as keep state earlier?
Keep state earlier. Latch. Mm. So keep state earlier means that means you told like sorry, you are telling like the S equals 0, R equals 0.
Yeah, miss.
So I'm little bit confusion here. So you asking why I'm not taking the this zero. So student, please mute your mic. So Putta, are you asking about why I'm not taking here 0 0 the is 0 and the R 0 in first option as the first option that you asking? I didn't get your question.
No, miss, I was asking whether
Hmm.
I was asking whether we used to call the keep it as a keep state, right? When both were 0, R, S and R, and now you're calling it latch. Did the term change, miss, for this flip flop?
Yeah. So the terms has changed. So we call it as the non-functioning. It's non-functioning. So in
So is it wrong if you say it's a keep state?
uh latch non-functioning. Yes, no, we can take the keep state as well. But I'm not sure. So it's better to use these things. Okay. So non-functioning means I think so it's also same as the keep state. Uh, but I'm not sure about that one. Keep state. Yes, so I will check and let you know, Putta. So here, so the when the clock signal is 1, then that means clock signal is provided, then the SR values are 1s, then it is we called as the restricted or the prohibited state. So then, so these are belongs to the when the clock signal is provided. So then the clock signals is not provided, then all become the latch. All state become the latch. So here by looking at this table here, these four belongs to the clock signal is not provided. The clock signal not provided. Then first four belongs to the clock signal. Uh, Provided. This is the clock signal. This is clock signal is not provided. So here, if the clock signal is not provided, the flip-flop is not working. That means latch. The flip-flop is not working. That means latch. Understood? The clock signal is not provided means the flip-flop is not working. That means it becomes latch. it becomes latch.
Miss, I'm sorry, this is a question regarding the delatch again. Is it
Yeah.
fine if I ask this now?
So you have put the message, no? To me?
Oh, no, Miss, I have another question too. So, in the notes, in the diagram you showed us, there's
Yeah.
only one input going into the D latch. But when I Google, like when I search it up online, it says that there's also an enable input in the
Yes.
D latch,
Yeah,
but it's
yeah,
not
yeah.
shown in the diagram.
Yeah, so we are not going to discuss that part here. That's the thing.
Oh, okay. Why
That's
not, Miss? I thought it was part of the circuit.
actually I don't know. I'm not actually I'm not the one who creates the slides.
Oh, okay, Miss. So, okay, so the enable input thing isn't there for the D
Yeah,
latch,
yeah,
but
yeah, yeah,
for the D flip flop, it's there in the form of the clock signal, right?
yeah,
Okay.
yes.
And just one more thing, Miss, what is the
Hmm.
D latch actually suppose? Can you give like a practical example in how it's used, Miss?
D latch. Practical example. Um, Actually, the both of how I can say. So actually, the flip flop and both latches are used for to store the bits, single bits. But when talking about the actual, the practical scenario, uh, how I can say. So we'll check Puta. Because when it's come to the actual scenario, this flip-flop and both latches are belongs with the registers in the microprocessor. So therefore, mm, mainly tier registers are used this flip-flops. Um, how explain that one? Um, okay, so please, so I will finish this lecture and then come to your questions. So here, we talked about the SR flip-flop, and then um, and I want to tell that if the clock signal is not provided, that means the flip-flop is not working. That means it becomes latch. Then the registers using flip-flops. So registers are used for different operations like storing data, loading data from multiple sources into registers, then performing operation on the register's content and write the resulting data value to one of potentially in many destinations. So these are the uh, the scenarios we use the registers for the different operations. So registers using flip-flops. Here you can see parallelly the SR flip-flop. Parallelly, this SR flip-flop are connected to create 4-bit register. These are the SR flip-flop. So those are connected to create 4-bit registers. 4-bit registers. So these 4-bit registers create using 4 1-bit flip-flops connected sequentially. Okay, so these are the 4-bit registers. So these 4-bit registers create using 4 1-bit flip-flop connected sequentially. So these are the flip-flop. So flip-flop, when it comes to the flip-flops, it store the 1 bit or the single bit. These are the 4 1-bit flip-flops connected sequentially. So whole circuit we called as the 4-bit registers. 4-bit registers. So this can be extended to 8, 16, 32 and 64 bit. 64 bits. Okay, so this is the end of the lecture 6. So how was your presentation? Can you share the the things with me? How was your proposal presentation? Lamai?
It was good, Miss.
Good. Okay. So so next week also the proposal presentation is will be conducted, and the so after that you will get you will have the mid exam. So for the mid exam, I think you will get the question up to lecture 6. That means including this lecture. Yes, then yes, then you will have the. So I think you did this logic gate simulation part 3 worksheets there. Am I correct? So please, student, please give a 1 minute. Okay, so that's all for today. So please go through. So those who finish presentation, please again go through the lecture from lecture 1 to lecture 6, and you will get the question from those, including the K map, Kano map, and those things, and including these logic circuits part 1, 2, and 3, and then the data representation, and also the first lecture. So please go through, and yes, and another one, stay safe. Okay, so thank you for joining. Have a nice day.
Thank you, Miss. Bye, Miss.
So Puta, you